In this video, we examine the wave functions of the stationary states of one-electron atoms. Hydrogenic wave functions describe the stationary states of hydrogenic atoms, that is, atoms with a single electron. H, hydrogen, helium plus, lithium 2 plus, and so on. The wave functions are given by psi of NLM of r, theta, and phi equals to r NL of r times uppercase Y Lm of theta and phi. The wave function depends on the three quantum numbers n, l, and m. Often a subscript is attached to m to indicate that its possible range depends on l. Psi is a three-dimensional function and set up in spherical coordinates r, theta, and phi, which describe the three non-translational degrees of freedom of a one-electron atom. R and L is the radial function. It is a function of r only, and only depends on the quantum numbers n and l. YLM is the angular function. It is a function of theta and phi, and is called a spherical harmonic. It depends only on the quantum numbers L and M. Both components of psi are normalized separately, so that the overall wave function is normalized as well. Also, R functions and Y functions are orthogonal, so that the overall wave functions form an orthonormal set. Let's write this out. For R, the normalization and orthogonality integral is integral from 0 to infinity of R n prime L prime complex conjugate times R and L times R squared dr equals delta n prime n times delta L prime L. Note that the integral contains the R squared factor. The right-hand side with the two Kronecker deltas is 0 unless the two functions are equal. In that case, n prime equals n and L prime equals L, and the result is 1, the normalization. For y, the integral is integral from 0 to 2 pi, integral from 0 to pi of y L prime m prime star y L m sine theta d theta d phi equals delta L prime L delta m prime m. Note that the integral contains the sine theta factor. Again, according to the right-hand side, the integral is 0 unless the two functions are identical. In that case, it's equal to 1 and gives the normalization. Together, r and y mean for psi the following: the integral from 0 to infinity, integral from 0 to 2 pi, and the integral from 0 to pi of psi n prime L prime m prime complex conjugate times psi NLM r squared sine theta d theta d phi dr equals to delta n prime n times delta L prime L times delta m prime m. Note the r squared times sine theta factor. If the two functions are identical, we again have the normalization integral that gives 1. Otherwise, we have the orthogonality integral, which gives 0. Let's look at the general forms for r and y. First, the radial function. Its general form is r of nl of r equals to n nl times l n minus l minus 1 2l plus 1 as sub and superscripts of rho times rho to the power of L times e to the negative rho over 2, where rho is a scaled radius that's equal to 2z over n times r divided by the Bohr radius, r0. The first factor in this expression is a normalization constant. The second is a polynomial function in the scaled radius, and it's called an associated Laguerre polynomial. The third function is just a monomial in rho, And the last function is a radial exponential decay function. Overall, R is a real function and only depends on n and L. Next, the spherical harmonic. Its general form is y of Lm of theta and phi equals to n sub L super m times p sub L super m of cosine theta times e to the positive I m phi. The first factor, again, is a normalization constant. It's the same for plus m and negative m. That's why I've put the magnitude sign here. The second factor is a function called the associated Legendre function. It depends on cosine theta. Last, we have a complex exponential function in phi. Although these are general expressions for calculating the wave functions psi, it's easiest to look them up in textbooks or online. Be careful though, as there is some variation in the notation and in the sign conventions for the various functions. Now let's look at a few wave functions with low values of the quantum numbers. First, the 1s function. Psi 1, 0, 0 equals to 1 over the square root of pi times z over a0 to the power of 3 over 2 times e to the negative rho over 2. The spherical harmonic is a constant, and the wave function depends only on the radius, rho. For rho equals 0, we get a non-zero value for the wave function. This means that the electron has a finite probability of being found at the position of the nucleus. This is not surprising, since the two actually attract each other. Next, the 2s function. Psi 2, 0, 0 equals to 1 over 4 times the square root of 2 pi times z over a0 to the power of 3 over 2, that's the usual factor, times 2 minus rho times e to the negative rho over 2. This function looks similar to the 1s function, except for an additional radial polynomial. Just like the s function, 1s function, it also is non-zero at the nuclear position, and therefore there's a finite probability of finding the electron and the nucleus at the same position. Next, the 2p0 function. Psi 2, 1, 0 equals to 1 over 4 times the square root of 2 pi times z over a0 to the power of 3 over 2 times rho times e to the negative rho over 2 times the cosine of theta. For rho equals 0, this function is 0. When a hydrogenic atom is in this state, the electron is never at the nucleus, even though electron and nucleus attract each other. The reason for this is that in this state, the electron has angular momentum, and the centrifugal forces keep the two particles away from each other. In addition to the radial dependence, we now also have a theta dependence from the spherical harmonic, cosine theta. Last, let's look at the 2p plus minus 1 functions. 2p plus minus 1. They are psi 2, 1 plus minus 1 equals to 1 over 8 times the square root of pi times z over a0 to the power of 3 over 2 times rho times e to the negative rho over 2 times sine theta times e to the plus minus I phi. M is non-zero, so now we have the complex phi exponential at the end. In contrast to the previous wave functions, this one now is actually complex. This list of wave function continues, with increasing values for the quantum numbers, the polynomial expressions for rho, and the trigonometric expressions in theta get longer and longer, but the overall structure of the wave function remains the same. In summary, 4 things are important. First, the expression for a hydrogenic wave function is a product of a radial function and a spherical harmonic. Second, the radial function depends on n and L only, and the spherical harmonic depends on L and M only. Third, both of them, R and Y, and the overall wave function psi, form orthonormal sets. And fourth and last, states with L equals 0, that is S states, have a finite probability for an electron being at the nucleus. For other states with L larger than 0, for example for p states, this probability is 0 due to centrifugal forces.